and you receive it, but you don't want to see it blurred. You want to see it sharp. So we do the sharpening of the image, right? So when something is very sharp, it means that you can take a pen and you can draw easily the border around it. It's very important in many of the applications of machine vision. Why? Because your robot arm should go and pick up something. In order to pick it up, I have to know where it is, right? Imagine I want to pick up the glasses with the robot arm. If I am not sure, I can pick up the whole eye out, right? So it's very important to have a very well-focused or sharp image. So we will talk about the sharpening of images in this course also.
But
it's another application. Yeah?
Yeah, do you need metadata for sharpening?
No. From here, of course, here I sharpen the original image, but the aim is that you have something like this in your hand and you try to sharpen it as much as possible.
So this image contains all the information necessary?
No, the thing is that you don't have it. You have to approximate it. This is how it makes it, the processing. Because if I already have it and I don't show it and later I show it, I didn't do any processing. I just show why it was available. The question is that you have this in your hand, you don't know anything else. And then you try to sharpen it as much as it is possible. In order to really convert this one to this that you see, you need to have the metadata, you need to have the whole raw data, which we don't have it. We will see in the course how from an image like this you can make it sharper. Why we need to do this? Because as I said, your Hubble telescope has already taken the photo and sent it to you. You don't have any metadata. This is all that you have. Even with the metadata, the biggest size of the galaxy, which is billions of years away from you, is 3 pixels by 3 pixels. I mean, you have to zoom, you have to sharpen many things anyway. And we are talking about an image which the capacity is a couple of gigabytes, tens of gigabytes. So it's already very, very high. Yes, sir.
So in terms of file size, let's say we have the color image,
Yeah.
and then we turn it into the grayscale. And from there I can have two options, let's say the blurred one and the sharp one.
Yeah.
How it's going to affect the file size. Because in terms of pixel quality,
Yes.
it's the same 8-bit, it's the same different
Yes,
tones of gray.
absolutely. Then my question to you would be that what algorithm of compression do you use? Do you save them as a BMP or do you want to save them as a JPEG? If you save them as a JPEG, they will have different size. If you save them as I don't know, TIFF, nothing will happen. They'll have all the raw data. So this will become much lighter than this one if you are using the right compression technique. And we will talk about the compression towards the end of this course, because before that you need to know a lot about many other processes. So when I tell you that why this one will have less space than the other one, it will become actually very default by you already. But we'll talk about them. Your questions all are valid. Another thing is that, well, we can detect the edges of the images. Because many times, especially in case of a machine, when it wants to interact with human or interact with something, what is very essential is the edges. I gave the example of picking up his glasses, right? His glasses from his face. So it's very important for me to know where are the edges of the handle so I can pick it up. Knowing the details that this is a Hugo Boss or this is an Armani, we don't care, right? We don't care much because it doesn't help me how to pick this one up, right? So this is a very important thing to be able to extract the edges. And when we talk the edges, you see that this is very much the way it helps us in order to convert an image like this into an image which is sharper. Okay? The other thing, the other process is that converting of a grayscale image into a binary image or so-called black and white image. Black and white image is an image that the quantization level of it is using 1 bit. You are either 0 or 1. Is it useful to have a black and white image?
Maybe for having the edges.
You can use it to calculate the edges, but it's a very expensive way to calculate it. Has anybody used a black and white image for some application? Yes?
I used to do 3D graphics, and I needed to make a bump map, so I got highlights.
You can use it in order to create mask. Any type of masking anywhere. Why? Do you know this stencil? Which means that there are on a piece of paper, you can make some shape, you can cut it, you can put it on the wall, and you can paint it. And when you remove the paper, you can see the shape. Why? Because you are masking some parts and you don't mask the other parts. That's why the height gets the whole thing. This creation of such a mask is used, these black and white images. It's like that somehow I have an algorithm which understands where he is inside this picture, and I want to just segment him out so I can create a mask which makes sure I am cropping him, nobody else, right? So it's very important. Another very useful application of that one is in biomedical imaging. Most of the images that we are gathering using the biomedical imaging is black and white or close to binary. You can have some tones, but I mean very, very low number of tones. And another thing that we will talk about is that, okay, all these examples that I provide, the source was a grayscale image. We can have a color image and do the things on the color image too. And this is something that we will also talk about inside this course. So basically, everything that you saw in here, we will learn it inside this course in detail. And there are just a few minor examples of digital image processing. There exists lots of more applications and lots of more processes that we can do on the images. Any question up to this point? No question? Now, from next slide till almost towards the end, we will talk about the physics of light and physics of how an image is being created. You are not responsible for it by any means, but it will be good to know what are the sources that can be used in order to produce images, right? We are surrounded by the electromagnetic waves, right? And these electromagnetic waves have from very small wavelengths to a very high wavelength. And practically we can say we have gamma rays, X-rays, ultraviolet rays, and we have a very narrow visible light. That's how we all see each other, right? And then it continues by infrared, microwave, and radio waves. Because all of them are of the same family, and we can only see by this small range, it means that actually everything can be seen by each of them. We cannot see it, it doesn't mean that we cannot create it. So, physically speaking, an image can be created by any of these electromagnetic waves. Some of them have a very low wavelength, some of them have very high wavelength. Which one has higher energy?
Gamma.
Yeah, the one which has a lower wavelength has a higher energy, and the ones which have higher wavelength has lower energy. This one kills you, this one makes you to listen to the radio, right? So let's start by talking about gamma ray. Do you know where is the application of the gamma ray?
Observatory space.
Absolutely. In aerospace industry, it's being used a lot in order to capture the pictures of galaxies, births of stars, deaths of the stars, and so on. And of course, it will be also used a lot in medical imaging, right? In medical imaging. The next one, X-ray. How many of you have broken bones? Very good. So you have a very excited. X-rays obviously can be used in biomedical imaging quite a lot. It's used in electronics engineering in order to find out if there is anything faulty on the PCBs, on the motherboards, and so on. And of course, it can be also used in remote sensing and astronomy, astrology. I don't know what's the difference between them, but those things in this space. Now we go to the UV. Any application of UV?
To cure 3D printed stuffs?
Yeah, it is a very good application, but what about application in image processing or image acquisition?
Detecting real money.
Yeah, you can check if the money is fake or real. You can use it in biomedical imaging. You can also use it in astronomy and stuff. What about visible light? I mean everything, everything, every photo that you are taking, the photos that you use, it's my cat. Even we can see her because of this visible light. What about the infrared?
Night vision goggles.
Night vision, it's called night vision. Infrared, what's the most famous application of infrared?
Remote control.
Remote control. But from image perspective, thermal photos, right? You can see what is the heat map, it shows the amount of heat and so on. Here is an application of it, so you can see if there is something live or not. And you can of course use it in the space technology. Now, I get back into here, you see we have, when we talk about infrared, we have two special range of this infrared. One of them is called near infrared, the other one is called far infrared. Why do we have this term? And
Like the infrared that we can see and the one that we cannot.
the one that you can see and the other one which you cannot see.
Well,
Who can see infrared? Which one of you can see infrared? I mean, you are the next Superman if you can.
With your skin.
So you can look at somebody and say, oh, you have something, or what can you do this?
you can feel infrared.
I mean, I use it, but not in that context. We can't. No, I mean, our eye, practically, biologically, we are not sensitive about the infrared. We cannot detect it. So, well, why do we use the word near IR? Look at here. You can see that everything is very continuous. In other words, there is no rigid definition to say that, okay, your wavelength is above 99 nanometer, then you are infrared. So if you are 1 micron below, you are visible. There is a range. There is a range that it stops working. That's why that in the cameras you cannot limit it. So it's because it's a physical property of the materials that you have in the sensors. And typically what happened, although you want it to stop by the end of the red, which is visible by human eye, you can go a little bit of the infrared. That's why that with your mobile phone, you can put it in front of your remote control. When you press it, with the phone you can see this infrared things is blinking. With the eye you cannot see it, right? So that's why that the near infrared is very, very useful. That's why that most of your webcam that you have this near IR, right? Near IR into it, so they will be able to see a bit of infrared also. So very useful application of it. You can use it for liveness detection. Like if there's an earthquake, you can use it in order to see if there are some live bodies still trapped somewhere and so on. We continue to microwave student life. So you should know microwave pretty well, right? I still use it also. But how many of you are with SQ? Okay, do you know any application of this microwave in SQ? It is used in something which is called SAR technology, synthetic aperture radar, right? It is used in order to produce a map of the Earth. So you can see the mountains, you will be able to see that there are forests, waters, some swamps and so on in there. And finally, the radio frequency. What's the application of radio frequency?
Communication.
In image processing, like image, which type of image does it produce? Yeah, maybe. I doubt because the wavelength is too big, but they're making. It has the biggest wavelength. So having a very big wavelength, what does it mean?
Low energy for communication.
Yeah, in low energy, it means that you are safe. You are not dead. So if it is safe and it doesn't kill you, so it means it has a very good usage. Where can it be? Biomedical imaging. I hope you will never use it, but if you have heard of MRI,
What is
Is-
MRI?
magnetic resonance imaging, And if you have a tumor or some cancer in your head, they put you into the CT scan and they make the map of 3D map of your head. And then they say, okay, this person has a cancer, not has a cancer, has this or that. So they are kind of acquiring, making the image out of these specific wavelength. Why? Because it is very, very safe. Apparently, if you are using our brain, it's apparent to be very important, so we don't want to damage it much. Right? So that's why they are using the safest possible wavelength. Now, as you saw, basically, space uses all of this wavelength in order to produce an image. In our textbook, there is an image from NASA, which has been produced of the same scene using different wavelength. So the same scene when you are using gamma, the same scene when you are using X-ray, it looks like invisible light, in infrared and radio. They look very different. I am not an astrologist, so I do not interpret them. However, an astrologist can sit down and tell you that, oh, okay, here is the birth of a star, or this one is the death of a star. Why? Because of this and that. So all of them can be used. Each of them are carrying some extra information to give some understanding to the human being or to the experts. Like here, you can use the visible light, which means that you can look at the face of the person and understand the person is in pain. So you understand that the person, as a doctor, you might understand that so something is wrong. And then when you look at the other same view of the person, but using other devices to acquire the images, then you will be able to say, okay, the person is in pain because there is a tumor in the head, for instance. So we look at the electromagnetic waves that are being widely used in order to produce images. Is there any other way of producing image?
You can draw.
Yes, that's a very, very good way, but do you know the ultrasonic devices? They use to see the babies, or to find out if there is a stone in the kidney and so on. And this one is totally different from the electromagnetic wave because it uses the sound. What's the difference between the electromagnetic wave and the sound? Nature-wise, they have very big difference.
Sound is over the air.
It's mechanical. It's mechanical. In the vacuum, you cannot say anything, or you cannot transmit it. So it means it has totally different source than electromagnetic wave. It will be used in order to find out if there is, let's say, as I said, stone in the kidney, because the body tissues are very soft and can pass through it. And as you can see, you can use it in order to produce these ultrasonic images for babies. Now, another thing is, so we know how the images are being produced. And as I said, we will only focus on this very small narrow bandwidth, which is the visible light. So all the course is about the visible light. We don't talk about any other ones. And in order to talk about that, let's talk slightly about the eye itself, the biology of the eye, right? I don't know when was the last time we took the biology, but you might know that our eye is made of a few parts, like lenses, pupil, and the retina, which makes, when you are seeing something, it reflected. It's called a small hole, right? A tiny hole that we have, and it put the picture on the back of the retina. What happened at the back of retina?
Cone cells and rod cells.
Yeah, we have two types of cells, cylindrical one and the cone-shaped ones. The cones are at the center and are surrounded by the cylindrical ones. Cylindrical ones are responsible for the intensity, and cones ones are the artistic ones, which knows the color. Right? So if somebody is colorblind, then the cone ones are malfunctioning or do not exist or something is wrong with them. And the cylindrical ones, which are surrounding, are the ones which are responsible, very sensitive to the illuminations, little bit of light. That's why that if suddenly you switch off all the light, you will not be able to see anything. However, if something is at the side, you kind of can see it, can feel it. Because when it is reflected, things which are at the sides are mostly goes towards the cylindrical, which are very sensitive to a little bit of light. Yes?
Does that mean that the spatial size of the image that we are seeing is actually quantified?
No. We don't. Everything is very analog in there. I mean, it's not like that we have. I mean, I don't know the biology, and there can be lots of doctors who say I am saying wrong, but somehow it is formed completely very analog. You cannot say that the resolution of my eye is 20 pixels or 50 pixels. I don't know how the whole that mechanism works, so I just know a little bit about the cells and so on. But what we see is all analog. Anyway, so we have this, which is around the eyes, which is very sensitive about the lightening, and the one which is sensitive about the colors are more in the center, and they are cone-shaped. So they are all seeing it, and they transmit it to the brain, and the brain does the rest of the magic, right? So if the eye works like this, so we can inherit this one and produce something which is called a camera, which has a lens, and we have something like a retina, and it will produce the same image. Now, because this camera that we have nowadays is a digital camera, so what we are producing is a digital image. Previous times, and maybe 20, 30 years ago, people used to have the analog camera, which you have to go and develop negatives, right? And then you would print and have the images. Now, when we are talking about that, in the retina, all these cells that we have, in the camera, we have something which is called image sensors. Image sensors are devices which they have special materials on top of it, that when the light comes, it will trigger them and it releases some voltages. More light, it produces stronger wave, less light, it will produce weaker waves. Now, because this is a physical and real world material, it means that the waves which are being produced are always continuous. It's not analog yet. However, the quantization happens on the reading of this. If you have a very sensitive device which can read the small changes, then you can have very high resolutions of high quantization values. That's why we have 14 bits. We have 12 bits cameras. And if it is cheaper and cannot understand the sensitivity, that's why we have 8-bit representation. So that 8 bits, 12 bits comes from how we can read this waveform. Now, in general, you can have this sensor being used in three forms. One is that you can use one sensor alone in order to read everything. Then if I have only one sensor, in order to read everything, it means I have to go every rows and every columns, right, in order to be able to read. The other one is that we can have everything in one line, then I can go from top to bottom in order to read, or I can have the array sensors, which it means that at one instant I can read everything, right? I can read everything. And here are a few examples of them. This is how these sensors works. You can have your image as it is rotating. If you read every row or every column till the image finish. What about the line one? Do you know an example of this?
Scanners.
Scanner, flatbed scanners or photocopy machines. What about this? The cameras. All the cameras that we have is here. And now, again, the technology has been developed so much that per inch you can have a lot of these sensors. That's why that now you have a camera which is, I don't know, 20 megapixel. Before we had a camera which was 4 pixels, you know? So these number of pixels which are being introduced talks about how dense you have the number of these sensors, image sensors there. So here are some examples. So what happens when you are having these array sensors is that you see an image in the real world, it will be sent through the lens of the camera on the back of the camera which we have the image sensors. Now, these image sensors, every sensor gets different amount of the light, so it will produce different type of voltages. And we are reading these voltages, then we understand that in some place it is this color, some places this tone, some places this tones, and so on. However, because we don't, when you put the sensors, between the sensors is empty. It means that if something is mapping there, it's gone, right? You can only read from the sensors. That's why that what the continuity that you see, of course it has been exaggerated, then you don't see this continuity because there isn't any sensor between these two pixels. Do you get it? Now, how many lines do I need to have in order to draw a circle? How many? Okay, let me read one more. How many straight lines do you need to have in order to draw a circle?
Infinite.
Infinity many, right? Because if this is a circle, right, with 4 straight line, this is the closest that I can get to a circle. With many more, I can go very small, and I can practically, if I have infinity many, I will have a very smooth ones. So here, you see that this is the smooth object, but when you put it on this dotted sign and on this array, you will start to have some jumps, right? Now, if you make it smaller, if you make these boxes smaller, then you see that it will become smoother, right? It will become smoother and smoother. So, the whole thing is that you have an analog, and from an analog you get a digital output. And in order to do that, in order to digitize something, we have to follow 2 very, very important steps. So, steps of digitalization are sampling and quantization. And this is something that we will talk about in our next lecture. Do you have any question? So, what we discussed till now was very general overview of what we see, a little bit of physics. If you didn't know or you didn't like the physics and examples, that's all okay. You're not responsible for it. It's just like for your information to know that upon what ground we are walking. Yes?
This is more regarding tech. So back in the day, we just had the negative, meaning it's kind of like a black and white image, because the negative is
not a black and white image. It's called a negative image. It is something that we will learn in this course, how to calculate a negative, and from a negative how to get the actual image. Yes?
So from a negative, you can't say it's just one tone of color, like it's different shade of that silver bromide or something of that sort, right?
Yeah.
How
It's
did
not.
they then?
It is not. But let's say
How did they process that?
because it is not.
Yeah, that was the question. Because how did they process that to an RGB?
Yeah, because they actually have captures based on the frequencies on those negatives that you are seeing. That's why how they know that this is gray, this is green, this is blue, this is red, and so on. And that's why if you take it towards the light, you actually see it in color.
Yeah,
Not in the
it's a weird.
Yeah, weird is the right word. But again, how this film development works, I'm a professor of computer vision. I really get much. I have enough money to pay them to develop it. And we don't talk about that one. It's more of the chemical, the properties of the chemical materials.
Yeah.
But what they have in there is not only the gray level. It is true color information inside.
Yeah.
Yeah.
One question regarding we saw that images on camera or infrared, but they're outside our visible spectrum.
Yeah.
So we're using the psychovisual effect.
No. Psychovisual is very different. Look, psychovisual is like you see and you don't understand you are seeing it or not seeing it. Those things, the X-ray, gamma, we don't see it anyway. It doesn't mean that it doesn't exist, but we don't see it. Psychovisual is like that. It's so much small detail that you don't understand. Have you heard this expression where somebody has an eagle eye? It means that the person who can spot out the very small details. I don't have an eagle eye, but because it means that psychovisually you can kill more details for me and I won't realize it. Oh,
So psycho-visual thing is about the actual mental image processing.
this is how human understands the image or feel the details. You can stop it. Yeah.